So we're going to talk a little bit about magnets and magnetism. Here's a magnet, and this isn't a very good example because this is a metal table and it seems to be affecting the way the magnet points, but the compass points, right? A compass is a tiny magnet that just aligns itself along the Earth's magnetic field. And so I can put a magnet near it, this is a magnet, and sort of affect its motion somehow. This is just a crazy little magnet, this little red thing I'm holding. And so you can kind of see that I can alter its world, the compass's world, by moving the magnet around. These aren't very good compasses, but you get the idea. So a magnet can attract bits of metal, like this one, or this one, right? Like that. It attracts some metals, but not others. So here's... let's see if I can pull these guys out of here. Here's a piece of aluminum. Here's a piece of copper. And here's a piece of something. Steel, maybe? Zinc. So, nothing from the zinc. Nothing from the copper. Nothing from the aluminum. But the steel works great. You can make a magnet with just a coil of wire and some and a battery. And so if I take this, so this coil of wire, never mind this piece that sticks out in the middle, here's a coil of wire here. It's just wrapped around this bolt, and the two ends of the wire are these two pieces. And so I can put one piece here, maybe, and then hold the other end over the other end of the battery. Now I have a current going through my battery, and watch this. I can kind of pick up that that little piece of metal. I don't know if you can see that, but I'm holding it. If I release the battery, it doesn't pick up anymore. And so it turns out that a current running through a wire produces a magnetic field. What's interesting about that is that that's how, very simply, almost all electric motors work. Electric motors are really very simple. They're just a magnet and a coil of wire and a battery. And that's why your grandmother has a refrigerator that's 400 years old, because the motion is so simple. That's why one of the reasons why electric cars are getting more popular isn't just because of the renewable energy, but because the motors are much simpler than internal combustion motors. And so there are lots of reasons for that, for the popularity of electric motors, for electric cars. And so we're going to talk about magnetic fields in this chapter a little bit. It turns out, I showed you this compass a little while ago, which isn't working great, but you can see it's sort of aligning with something. It's I think they're just some local, this panel is metal, this whiteboard is metal, and I think it's somehow magnetized, because if this was looking at the Earth's magnetic field, it would be pointing this way, which it almost is, but it's kind of varying around. So I can't decide what the situation is. What if I got it up on here and set it like that? Nope, that's not working. Well, I don't know, maybe. Yeah, actually that looks pretty good. From where I'm sitting, that way is north. And so it looks like this little silver end of the needle is pointing to the north. And so once again, I'll try bringing my little magnet over here and seeing if I can mess with it. Yeah, see, now I've got a little better control over it. So if I flip this over, I should get the silver end. Maybe not. All right. Anyway, that should be the. So the Earth is a magnet, right? Just as we have positive and negative charges, magnets have two poles, north and south. I don't know if these guys are labeled. I don't think they are. Yeah. So here's a magnet, and you probably can't see it, but that's the North Pole and that's the South Pole. So maybe I can see which one of these points that way. This is just not working the way I want it to, so I'm just going to let it go. Magnets have two poles, a North Pole and a South Pole. They got their names because so if you allow a magnet to just point in any way it wants to, like you hang it from a string, or sometimes you can put it on a little piece of wood and float it in water, so it's free to. If you make it free to turn, it's the North Pole of the magnet will point north, and what that means is that means that the Earth is a magnet. And since opposites attract, since the North Pole of a magnet points towards the Earth's North Pole, that means the Earth's North Pole is a magnetic South Pole, if you get what I mean. And so if this is the Earth, right, and here's the North Pole, so this is Santa Claus's house, right, that's the North Pole. Then the Earth it's like it has a little bar magnet inside, and this is the South Pole of the bar magnet, and this is the North Pole. And the magnetic field lines look like this. And we'll talk about them more as we go. The Earth's magnetic field plays an important role in the Earth's habitability and how its atmosphere behaves and all kinds of different things. It turns out the Earth's magnetic field protects us from cosmic rays, from high energy particles from the sun. It protects our atmosphere and us. So and it's true for all planets. The magnetic field kind of protects the planet from high energy particles. I mean, it's not necessarily trying to do that, but that's the effect it has because of how charged particles move in magnetic fields. It doesn't allow them to just use their energy to strip the atmosphere away or just to bang into things on the surface. It causes them to travel in spirals and lose their energy very slowly. So that's a little bit about the basics of magnetic fields. A charged particle moving in a magnetic field experiences a force F equals Q V cross B. So Q equals the charge. So its electron, its charge is minus 1.6 times 10 to the minus 19th coulombs, but its charge could be anything, of course, it could be any particle. V equals the velocity of the charge. B is the magnetic field. And F is called the Lorentz force. I think it was H Lorentz, but I can't really remember. And so The SI unit for magnetic field is Tesla, and if we just do the magnitude of these things, we would say F is equal to Q V B sine theta, or we just say F equals Q V B sine theta. This has no units, and so we could say for units, B equals F over QV, right, which is it's newtons over coulombs meters per second. And so that's a Tesla, vice versa. So let me just do a few examples of those. So I've got a charge Q, and it's traveling at 2,000 meters per second, and it's living in a magnetic field that's pointing straight down. Right. And so the little X's mean you're looking at the tail feathers, and so that means the vector is pointing into the board. And so the force by the Lorentz equation is QV cross B, and so the magnitude of the force is equal to QVB sine theta, which is equal to 2 times 10 to the minus 6 coulombs times 2,000 meters per second times 20 Tesla times the sine of, so if the velocity is this way and the magnetic field is that way, it's 90 degrees. Sine of 90 is just 1, and so that's 2 times 2,000, which is 4,000, times 20, which is 80,000. So 8 times 10 to the 4th times 10 to the minus 6th. And it's Tesla times coulombs times meters per second, and times sine of 90, which is 1. And so this is 8 times 10 to the minus 2. Now we just said that a Tesla was a Newton per Coulomb meter per second. And so if I multiply that by Coulomb times meters per second, I just get newtons. And so it's 0.08 newtons. And the direction of the force is, I put my hands in the direction of velocity, I curl my fingers towards the B, because it's V cross B, and stick my thumb out. So right, if that's north, which was what we said, then the force is west. Notice if the charge were flipped, if the charge were negative, the force would be flipped also. So if you do that for your right-hand rule and the charge is negative, you'd say the force would be to the east. If I swap that out with a charge of minus 2 times 10 to the minus 6 coulombs.